Hey, hope you're enjoying your cold day at home. We're going to be talking about section 5.3. The 5.3 is about the fundamental theorem of calculus. So this is the big payoff that we've been kind of waiting for. We've been talking about areas under curves for a little bit. We're going to kind of put that all together now. So remember when we talked about a definite integral in the last section, we said that that was just a number, right? The integral from a to b of f of x dx is just equal to some quantity. Right, that's just equal to some constant. What we're going to do is we're going to create a function in terms of x. So here we say g of x is equal to the integral from a to x of f of t dt. So what this is like the area under f of t dt starting at a so far. So when x is 1, we're going to 1. When x is 2, it's going from a to 2. When x is 5, it goes from a to 5. So these are going to be a function now, right? Because there's a variable assigned to how far under the curve we're going to be considering. So let's take a look at a real example. So let's say we have g of x equals the integral from 0 to x of f of t dt, and we're going to find the points for g of 0, g of 1, g of 2, g of 3, g of 4, g of 5, and then try to sketch a graph for g. So g of 0, well, clearly that's the integral from 0 to 0. We know that that's 0 because there's basically a rectangle with 0 width. So 0 to 1 is like this part right here. Well, that's just a triangle. So the width of that triangle is 1, and the height of that triangle is 2. So 1/2 base times height gives us an area of 1. And now from 0 to 2 is like that shape. So it looks like the g of 2 is the g of 1 plus the area of this rectangle. So I know that that's going to be the integral from 0 to 1. That's g of 1 plus the integral from 1 to 2, which is just the rectangle. So that's a width of 1 and a height of 2. So we already found that g of 1 is 1. And then this is 2. So 1 plus 2 is 3. So g of 2 is 3. Now for g of 3, we have the area to here. Now that's the triangle from before. That's the rectangle from before. But this new piece is curved. So we're just going to make an approximation here. So this to me looks like about 1/2. And this looks like maybe 0.8 of a box. So that's like 1/2 a box, that's 0.8 of a box. If I add those two together, I get about 0.1 or 1.3. So again, g of 3 is the previous box, g2, plus this new integral, which we approximate as 1.3. So 3 plus 1.3 is 4.3. And then to 4 is this much of our curve. But remember, when we have things below the curve, that's negative. So if I look at this, there's my triangle, there's my rectangle. So again, we know that that's 3. We know this part we said approximate was 1.3. If I look at this piece looks like the same shape as this one, and just one is below the x-axis and one is above. So I'm just going to make this is my g of 3, and I think that we said that this part was 1.3 for g of 3, so this part is just going to be negative 1.3. So we add those together, we get 3. And then our last shape is the whole shebang. So again, this was our triangle, that was our rectangle. We approximated this to be 1.3. We'll approximate that to be negative 1.3, and we'll approximate that to be negative 1.3. But we know all the way to here was 3, and then a negative 1.3 gives us 1.7. So let's take those points and let's plot something with them, right? So we had 0, 0, we had 1, 1, we had 2 was 3, 3 we saw was 4.3, 4 was back to 3, and then 5 was down to 1.7. So that's like a little curve that we might sketch. Is everybody okay with that? So we might ask ourselves, is there a relationship between G prime and f of t that we're just doing the function of, right? So again, this is our function f of t, and then this is g, so we're talking about the derivative of g, right? Well, here's our function for f, remember? Or here's a function for f, right? So this isn't specifically the f from above. This is like we're talking about the derivative here of this g and then this function f. Okay? So here is some arbitrary f of x. And then remember, g is the area under this curve. So in order to compute g prime from the definition of a derivative, we observe that h, the distance from one x value to the other x value, is always going to be positive. So g of x plus h minus g of x is going to be obtained by subtracting the areas. So it will be like the area for g of x plus h all the way to there, minus the area for g of x, which leaves only that little rectangle that we have illustrated, which is approximately going to be the distance between x and x plus h, which is h, times the height of the rectangle, which is f of x, because we're going to use a left area or left Riemann sum here, as that's our kind of our standard. So that's approximately this. So if I divide both sides by h, I get that f of x is approximately the slope, right? The slope of the line from here to here. And intuitively, we would expect then that if I take the limit as h goes to 0, that should stop approximating f of x, but should equal f of x. Now that's our big payoff. That leads us immediately to what we'll call the fundamental theorem of calculus part 1. So if f is continuous on the interval from a to b, then the function g, defined by g of x equals the integral from a to x of f of t dt, that's exactly the function we started with talking about, from a to b, is continuous on a to b and differentiable on the interval ab, and here's the kicker, that the derivative of g of x is equal to f of x. So if we look at this using kind of our Leibniz notation that we're accustomed to doing, if I take the derivative of the integral of f of from a to x of f of t dt, I get just f of x. So what we're saying is that the derivative cancels out the integral, and the variable from our integration becomes the variable on our function. So if I want the derivative of g of x, the integral cancels out, and this t becomes an x. And we're done. That's all we're saying. Done. Mr. Kulik, that seems really too easy. Well, that's the idea with the fundamental theorem of calculus, is that derivatives cancel out integrals, and integrals would cancel out derivative. But there's one thing we have to be a little bit careful on. What if this isn't just x, but a function in terms of x? So what if we have, say this one, the derivative of the integral from 1 to x to the 4th secant of t dt. So this is a little bit different because this is a function now in terms of x. So this is like a chain rule problem, right? So remember way back when, if we have the function f of x, or f of g of x, you can do something like let u equal g of x. So that becomes f of u. So the derivative then becomes the derivative of the outside times the derivative of the inside. Or we could write this as just u prime. So we'll have to do the same thing here. So this becomes secant x to the 4th, and then we have to do times the derivative of x to the 4th. So we get that this is 4x cubed secant x to the 4th. Everybody happy there? I hope so. Okay, but it gets better. It gets better. Now for the big payoff. Fundamental theorem of calculus part 2. So this is going to connect these ideas of areas under curve with the idea of the antiderivative that we talked about in section 4.9. Yeah. So here it says if f is continuous on the closed interval a, b, then the integral from a to b of f of x dx is the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. So this is now connecting this idea of the integral back to the antiderivative. So let's do a couple of examples. So here, I want to start, my f of x is e to the x, right? And I remember that the antiderivative of e to the x is e to the x. So this is going to be e to the x, and then usually what we do for notation is we draw a vertical line, and then we put the lower bound and upper bound, which tells us then we're going to evaluate this at 3 and subtract it from the antiderivative evaluated at 1, and this is our answer. Now the natural question be like, Mr. Kulik, what about the plus c, right? When we do the antiderivative, isn't there a plus c? Sure, yeah, that's fine. But if we do that, we'd have plus c here, and then minus e to the first plus c there. And when we distribute that negative, The plus c's and minus c are going to cancel, and we're left with the same thing. So usually when we're doing what we call a definite integral, we don't bother with writing a plus c. We'll look at when you do need a plus c a little bit later, but for these ones where the upper and lower bounds are finite numbers, or just just actual numbers even, we don't need the plus c. Okay. So let's look at the next example here. We're asked to find the area under the curve of the parabola y equals x squared from 0 to 1. So I'm going to rewrite this as an integral. So the 0 to 1 is my a and my b. This is like my f of x. Remember, we always have a dx at the end of our integral. So the antiderivative of x squared was add 1 to the exponent and divide by the new exponent. We evaluate that from 0 to 1. Again, because those are the bounds of my integral. I plug the upper bound in and subtract the lower bound. I get 1/3. Let's do another. So here we're doing the integral from 3 to 6 of dx over x. This looks a little weird, but I think if we rewrite it this way, it looks a lot more familiar. So the first thing I want is the antiderivative of 1 over x, which we should recognize as the absolute value, or the natural log of the absolute value of x. And we're going to evaluate that at 6 and subtract it from 3. Now I'm plugging in 6 and 3. I'm dropping the absolute value because, well, the absolute value of 6 is 6 and the absolute value of 3 is 3. So this is the natural log of 6 minus the natural log of 3. And if I wanted to feel fancy, I can use my quotient rule for logarithms to rewrite that subtraction problem as a division problem. And 6 over 3 reduces to 2. And probably that would be the answer that would be listed in the back of the book or in a non-calculated multiple choice question. Okay. So here it says find the area under the cosine curve from 0 to b, where b is between 0 and pi over 2. Now this is important because if I remember the graph of cosine, from 0 to pi over 2, it's always positive. So that's the part that I cared about. I just wanted to note that. If it wasn't positive, we'd have to do quite a bit more on this, but this makes life very easy. So we'll set up our integral because we're looking area under the curve. So 0 to b, again, that's my upper and lower, and then my function is cosine x dx. So we'll start by doing the antiderivative. The antiderivative of cosine is sine. And we're evaluating from 0 to b. So we do sine of b minus sine of 0. And I remember that sine of 0 is just 0. So I'm left with just sine of b minus 0, or sine of b. And I'm done. So, in summary, the fundamental theorem of calculus has two parts. It says that the integral and derivative cancel each other out. So specifically, if I take the derivative of this g of x, the integral cancels out. So the function on the inside becomes my derivative with the new variable, so you might have to apply a chain rule. We saw an example of that. And then the second part of the fundamental theorem of calculus says that the definite integral I can calculate by just doing the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. And that's it. So much simpler than calculating the area under the curve using a Riemann sum and a limit and using all the summation formulas. And we connected this now back to that antiderivative idea that we were looking at way back in section 4.9. So that's it for today. Important section, but relatively simple, I think. So for the homework, you guys can work on these guys, and we'll take questions from both 5.2 and 5.3 next time. Don't worry about a 5.2 homework quiz. I'm not going to do that. We'll skip that. I would say just worry about a 5.3 homework quiz. So worry about these questions here. And we'll take questions from homework from anything you want once we're back outside of this polar vortex. All right, have a good day. Enjoy your day off. Get some rest. Do some work.